Hi everyone. Thanks for coming to this session. This is the last session for today. You are probably quite tired, but we have a very interesting session for the end. And I would like to introduce Krystsina Miatlovich and Mikalai Surta with their subject of machine learning technologies in face recognition. So you have the floor.
Good afternoon. We are here to take you to the world of machine learning and face recognition in particular, and we would like to share our experience of developing such a system. We represent IBA Group, one of the largest IT service providers in Central and Eastern Europe. It's headquartered in Prague, but its major development center is located in Belarus, Minsk, where we are from. So let Mikalai introduce himself first, as he was actually the initiator of computer vision studies in our department.
Okay, I'm a software architect with around 10 years of experience in computer vision and big data technologies. And my current focus is Hadoop technology stack and also computer vision research. And all those directions there were fascinating. And today I'm going to share my experience in computer vision.
My name is Krystsina. I'm a software developer specializing in computer vision, including face recognition, object detection, and image classification. And my other spheres of interest are big data and cloud. Today we'll be talking about face recognition in various aspects. We'll discuss how face recognition works, including architecture of neural network. We'll talk about the training process that we use to train the model that we use in our system and how we evaluated its quality. We'll describe the overall architecture of our system and talk about legal aspects connected with collecting and processing of personal information. So let's begin and discuss how recognition basically works. So when I first joined the team for a recognition project, I knew nothing about it. Well, I thought first you need to find faces. Let's say it can be done by shape and color, but how to determine who they belong to? My first thought was the relative position of eyes, nose, lips, and so on, and I even tried testing these hypotheses, but unfortunately I was stubbornly recognized as Mikalai. And that's when I got caught up in a fascinating research. I learned there are various algorithms for face detection and convolutional neural networks for face recognition. But first things first. So we have the task of automatically marking people in the photo. We have some training data set as well. And obviously the first thing to do is to detect faces. The most popular image processing Python libraries, OpenCV and Leap, offer algorithms for face detection based on patterns and deep neural networks. And personally, we prefer a histogram of gradients method by Leap because it's accurate, as you can see, and fast both on CPU and GPU. So we have found faces. An image is essentially a set of pixels, thus theoretically we could use this pixel vector as an input for a classifier to compare it with other faces in the database. Obviously there are reasons for not doing this. First of all, because in addition to the face itself, in the detected area there are background pixels that do not characterize the face itself. Secondly, the result will be affected by tilting or turning the head, and the most important thing is that the size of this pixel vector is so large then that classification itself will take an unreasonably long time or even fail. Convolutional neural networks solve these problems. They convert an image into a feature vector which is small enough and can uniquely identify a face. We'll talk about convolutional neural network later, and after we extracted feature vector, we can compare it with other feature vectors in the database by using a classifier, or make do with simple calculation of distances between vectors and identify a person by the closest vector in the database. So let's go back to the original data and perform all of the above steps. First of all, we processed all the labeled images, cropped and aligned faces, used a neural network to extract features, and fed these features to a classifier to train it. After that, we detected and pre-processed faces on the original image, extracted feature vectors from them as well, and used the classifier to label them.
All right, I now understand how basic face recognition works, and neural network is the key of all this recognition process. So let's talk about convolutional neural networks. Convolutional neural network is a type of network which was specifically designed for data with grid-like topologies such as images. The basis of this network is convolutional layer. The idea of this layer is that we take a filter, which is the matrix of fixed size, and we superimpose this matrix onto every possible position of the source image. And for each position, we calculate one value. The idea of this convolution is to find specific patterns which exist in original image, and if the result of a calculation is a large number, it means that this fragment of image has this pattern. Subsequently, we superimpose those patterns one over another, and we, as a result, get a feature vector which can be used to distinguish one face from another. We took several models from open source libraries such as OpenFace and DeLeap, and we retrained those models with our data sets and made some changes as well. OpenFace library has model has 50 convolutional layers, and the DeLeap model has 29 convolutional layers. And OpenFace library is actually developed using the Keras framework, so we could directly proceed to retraining this model. And DeLeap was for DeLeap we had to train and build our own model based on open source code that we found.
So, how does a neural network know what patterns to look for? Indeed, weights in the beginning, weights are initialized randomly, and patterns will be defined in the process of training a model. To train a neural network, you need to proceed from what you want to achieve. On a large number of samples, you need to show what you expect to get as a result. Having an input and an expected output, the neural network will rearrange its weights so that the actual output is as close as possible to the expected one. Speaking in terms of a neural network, at each stage of training you try to minimize loss function, which characterizes the extent to which actual output is different from the expected one. Obviously, training a neural network requires a lot of data. DeLeap developers, for example, used 3 million photos to train their model. We will need photos of several people and several photos for each person. Microsoft Celeb dataset perfectly suited our needs because it has 1 million photos with an average 10 photos per person. We pre-processed all of the images in the dataset, cropped and aligned faces, and resized the images to the desired size. Finally, we came to the most difficult and crucial part in training, selection of training parameters and loss function. We spent some time on trial training with various combinations of these settings, but unfortunately we got accuracy much less than the initial one. Then we realized that we still need to go a few steps, and we decided to try triplet loss function, which is described in many papers dedicated to face recognition. And its essence is as follows. If you want the resultant feature vectors extracted from 2 photos of one person to be as close as possible, you need to give a neural network 3 inputs. 2 photos belonging to one person and the other photo of some other person, and determine loss function so that it would generate a large number for large distance between positive samples and small distance between negative samples. And since neural network tries to minimize this loss function, as a result we will get vice versa, small distance for positive samples and large distance for negative samples. Still, this wasn't enough to improve the accuracy of the original model, and we realized that we need to form these triplets not in a random way as we did before, but so that the neural network could cope with the most difficult cases and distinguish between different people who look really alike to each other, or determine that similarly looking photos differently looking photos belong to the same person if they do. So now we formed triplets by taking two mostly dissimilar photos of one person and some similar photo of some other person. And now it worked, and we managed to increase the accuracy of the original models. So to summarize what we did to train the model, we found and downloaded dataset, sorted out part of the dataset, preprocessed all the images in the dataset. We used the original model to extract features, calculated distances between these features, and formed triplets based on the obtained distances. Then we loaded the original model with weights, supplemented it with 3 input layers and 1 triplet loss layer, launched training process, and evaluated quality.
In order to understand if results of our work were good or not, we had to run tests on both original model and retrained model. But before giving you any numbers, I'd like to make sure that we all understand the difference between face verification and identification. And also we understand the conditions in which all those numbers were calculated. So let's start with verification task. A verification case is it's when you have 2 photos and you need to identify is it the same person on 2 photos. When you take most of recognition libraries, they usually indicate the verification accuracy. And this number is usually high. For example, the LEAP library claims to have 99% accuracy. OpenFace claims to have 33% accuracy. And also you need to understand that the accuracy depends on the dataset on which the tests were done. The most popular dataset is LFW dataset. In our case, we run tests on the same dataset for original and retrained models, and got slightly better results than the original model, and you can see those numbers on this confusion matrix. But in real life, not always you need verification. In most cases, the more interesting task is identification. Identification is the case when you have multiple people in your database and you take a new photo and you need to identify this person on this photo. And calculating accuracy for such case is even more ambiguous because it's influenced by many factors, such as a number of people in database, presence of strangers in your data set, and also number of photos per each person in the database. We run tests for the same model on the same data set. We took not the same data set. We took photos of 1,000 people, and we took 10 pictures of every person, and also added some strangers. And the accuracy of identification was 91%. So that's the same model, but now we're talking about identification. And 10 times increase of number of people in database led to 5% decrease in accuracy. And as we also had some strangers in database, so we can say that these are numbers that you can expect to have in real identification system.
So the most obvious face recognition use case is recognizing people in a video stream and not in individual photos. We decided also to continue our research in this direction and wanted to see the performance of such a system in real conditions and try to recognize our colleagues. We put a stand in the dining room because this is the place where a large number of employees gather. And there are 2 cameras on the stand, the video stream from which is processed real time, and when an employee approaches the stand, the system recognizes and greets him. If a person was recognized incorrectly, he has an option to enter his name, and the classifier is retrained. Furthermore, having accumulated a sufficiently large amount of data on correct and incorrect recognitions, we have a chance to retrain the neural network itself to generate better features. So then the employee has the option to evaluate the work of the dining room, and as an emotional bonus he receives an assumption of system about his mood. We trained a neural network for emotion recognition as well. So recognition in a video stream is more than recognition in individual frames and then concatenating these results. For recognition to be as accurate as possible, we need to aggregate recognition results on neighboring frames, and realizing all this, we started to design our own architecture, and we decided to have some simple services, each of which performs its own microtask. For example, in the first version of our architecture, a frame is subsequently processed with cameraman, streamer, detector, recognizer, and AMP classifier, and the results are written to the raw recognition table. Limiting ourselves to only these 5 services would mean that we do not aggregate results and try to recognize people in individual frames, and hence do not use the advantage of recognizing in a video stream. Therefore, the next service in the pipeline is aggregator. In the raw recognition table, we have data on recognitions, including timestamp, face coordinates, and feature vectors. And with this data, we can combine recognitions from neighboring frames and to define objects that represent real people in the video. So these objects are stored in memory, and if every new face can be either attributed to one of these objects or be marked as a new one. Aggregated results are written to the recognition table, and the notifier service monitors changes in the aggregation in the recognition table. And if there are new faces in a frame or there are some differences in old objects, it sends a signal to the web service and UI is updated. As a result, we got a system working in 2 networks. In addition, we constantly needed to access IP cameras, 2 IP cameras, and the need to transfer images over the network, and a large number of links in our architecture led to a performance problem. And so we tried solving this by reallocating services between networks, getting rid of system writes, combining multiple services into one to eliminate the need for data transfer and intermediate tables in the database. Before evaluating performance, we must say that performance is influenced by many factors, such as number of faces in the frame, minimum number of subsequent recognitions that we consider enough for making a conclusion, image quality, which influences in both directions, and number of just recognized people further processed by aggregator. So we evaluated productivity of the system, and we got 1 second, and this is the minimum time in ideal conditions that are unlikely to be observed in reality. So 1 second is much. Then we realized that we need to work on the second version of the architecture. And at first glance it may seem that it is different from what we had before, but actually these 2 architectures have much in common. Aggregation here is performed by face tracker, which task is to detect bounding boxes, assign unique IDs to each bounding box, and establish correspondence between bounding boxes on neighboring frames. Frames for each bounding box are sent over to face recognition engine until we get the number of recognitions that we consider enough to make a conclusion. Core changes in these two architects are the way the data exchanged between services and the way the aggregator works. For example, in the previous version of our architecture, we compared faces by face coordinates and feature vectors. But in the second architecture, we realized that just coordinates is enough, and this allowed us to use the significant reserve for increasing productivity, because now we don't have to recognize every frame, but do it when needed. Also, instead of having one large object with history, now each bounding box has its own local history, which helped with performance. And we got rid of re-aggregating results, because in the first version of the architecture, aggregator, for example, put records for the last 10 seconds and it worked 1 second, and hence the intersection of time windows was 80%. And this time we were pleased with the result. And from the moment when an employee approaches the stand and to the moment he sees his name in UI, an average of half a second passes. The most important thing in our modifications was not to lose accuracy while increasing productivity. So for the 5 months of application's operation, we have collected statistics on correct and incorrect recognitions. So there have been 2,355 recognitions, of which 347 times employees indicated whether they were recognized correctly or not. And the overall percentage of accuracy is 92.7%, which is expectedly different from verification accuracy that we discussed earlier. Among the people who are known to the system, 93% were recognized correctly, 5% were recognized incorrectly, and 2% were recognized as unknown. At the same time, 92% of unknown people were recognized correctly as unknown, and 8% were recognized as one of the known.
As we discuss the topic of face recognition, it's important to touch on the legal aspect of processing and storage of personal data. Of course, in order to train a classifier, we had to use real photos of our employees, and we got those photos from corporate database. Photos get into this database when people apply for a job, and also when new people come to our company, they also agree that the company can use the photos for internal usage. And also it's important to mention that when we receive new frame, we do not store this frame itself in database. We only extract feature vector and we store this feature vector in our database. And having this feature vector, you cannot identify person if you don't have access to the original model which generated this vector. So it's impossible to identify the person outside of the system. And also, unknown people can only be identified if they willingly enter their name in our application. If they do not enter their name in application, then we even do not store or extract feature vectors. Also, we installed our application stand in such a place that employees can always pass by without being captured by cameras. And also we put large note which explains the purpose of cameras and so that everyone understands what's going on. And we also distributed this information across our internal social network and other corporate resources. So we believe that we made everything possible to make sure that we do not violate any rights of our employees.
So the results of our research showed that the problem of person identification is far from being solved, and although it's easy to determine the owner of a mobile phone, it's still difficult to identify a person in the crowd. However, such face recognition systems allow automating of processes such as finding a person, among others, or verification personality. And in conjunction with human mind, it can give excellent results. Still, we see two ways of improving accuracy. The first way is hardware improvements, both for cameras to obtain better quality images and for graphics processors to process them. We can say that modern equipment is still not fast enough to process all the frames in the video stream, or if it's fast, its price is still high, and it eliminates its need in real scenarios. And the second way is to improve the architecture of a neural network itself, to prepare better data sets, to come up with better ways to train a model. And as a result of our study, we showed that this can be possible by retraining the existing open source models and improving them. So we hope that we inspired at least some of you to work on even better solution.
Thank you for your attention. We're glad to answer your questions.